We're going to talk about titrations, and titrations are based on neutralization. So when you combine an acidic solution with a basic solution, your H plus and your OH minus are going to become equal. So your general formula looks like this: acid plus base yields a salt and water. Now, salt is not always sodium chloride. It can be any ionic compound. Remember, they're going to be electrolytes, and they break, so they conduct electricity when you dissolve them in water. So our learning target, we're going to use stoichiometry. All right, we're going to interpret titration graphs here. So a titration is a lab method for determining the concentration of a solution. We're going to use a solution that has a known concentration, and we're going to use our stoichiometry, our mole ratios. Now, equivalence point is where your neutralization has happened. H plus equals OH minus. End point is where you see a color change in your experiment. All right, and these two should be very close. Now, we have an example, and here it is. All right, so we're going to use stoichiometry for this. So here's our balanced equation. Now, we know that we have 89.2 milliliters of 0.76 molar NaOH, and we have 50 milliliters of HCl. So we're trying to find the molarity of this HCl that's going to neutralize our sodium hydroxide. So for our conversion factors, we're actually going to use our molarity formula. Okay, so we can use the molarity and the volume to find moles of NaOH. Okay, so that's going to be 0.06824. Remember to change milliliters to liters there. We're going to put our fractions in. These are 1-to-1 mole ratios. So notice that we have the same number of moles here because we have the 1-to-1 mole ratio. Now we're going to plug that back into our formula with our 50 milliliters of HCl, and that's going to give us the concentration. So 1.36 molar is required to neutralize this amount of sodium hydroxide. Now, here's our next example. We have 40.8 milliliters of our sulfuric acid. We've got 50 milliliters of KOH. What's the concentration of the base? Now, here's our formula that we're going to use, our equation. So what do we know? We know 40.08 milliliters, 0.106 molar H2SO4. We have 50 milliliters of KOH. We're trying to find the molarity. So we're going to use our molarity formula for our conversion factor. So we solve for moles here. We get 0.00432. Now, when we put in our fractions, notice that we have 2 over 1 here. So our moles of KOH is 0.00864 moles. So we use those moles with our milliliters here. Remember to change them to liters. So my answer is 0.173 molar KOH. Titration curves, we're mostly going to look at strong acid, strong base. This is when you measure the pH of, like say an acid. Well, here we're starting with the base, and as you add acid to it, you record the pH. So the end point you need to mark, all right, end point is going to be right at 7. It's going to be right in the middle of this steep curve. So look for the steep curve, and that's where your end point is going to be. Now, when you have a strong acid and a weak base, the end point is going to be a little bit lower than 7. When you have weak acid, strong base, it's going to be a little bit above 7. And weak acid, weak base, there's a lot of buffer action that happens. So you have a gentler slope, and your pH is going to be right at 7. Indicators are dyes that change color in a specific pH, and we're going to use those to determine the endpoint of a titration. Okay, so they're going to change colors when you put them into solution. This is a graph of some different indicators. They do change over different pH ranges, which is good that you can use those for different types of solutions. Litmus is here in the middle. You usually use litmus paper sometime in middle school. Phenolphthalein is another common one that's used in lab. But you can see that the indicators give you a nice, pretty little rainbow. This is especially useful in your blood. You create buffers. They're going to resist changes in pH. So you don't want your blood to change pH very much. It's slightly basic under normal circumstances, but you don't want it to get too acidic, and you don't want it to get too basic. So your body is designed to absorb some changes, like you eat acidic foods, the carbon dioxide that you breathe in, all right, can change your blood to acid. So there's lots of different applications that you can use this for.